Hello and welcome back to the channel. Today we are going to start with interpolation. So interpolation is the process of estimating unknown values that fall between known data points. And it is widely used in numerical analysis to construct new data points within the range of discrete set of known data points. So if we take its definition, mathematically it will be like that we are given a set of data points that starts from x0, y0 and then it continues like x1, y1 and then goes up to xn and yn. These are the set of known data points. Interpolation is the process of finding a function fx such that fxi equals yi, that is for I equals 0, 1, 2 and that continues up to n. Interpolation is also a process of estimating fx for some value of x that belongs to x0 to xn. Applications of interpolation are in estimating values from experimental or tabulated data, computer graphics and animation, data fitting and prediction models, and lastly solving differential equations numerically. Next is assumptions in interpolation. So interpolation methods relies on few key assumptions. The first one is that the function is being interpolated is smooth and continuous in the interval of the interest. Next, that there are no significant errors or noise in the data. Third assumption is independent variable x is either equally spaced or known precisely. The fourth and the last assumption is the function varies gradually and does not exhibit extreme oscillatory behavior between points. And violation of these assumptions can lead to large interpolation errors. Looking at errors in polynomial interpolation, when using interpolation, especially polynomial interpolation, it is important to estimate the error involved. So error formula or the general polynomial interpolation formula for error is Ex equals Fx minus Pnx equals F to the power n plus 1. Then we have this symbol and divided by n plus 1 factorial. Then we have it from I0 to n x minus xi, where p and x is the interpolating polynomial of degree n and this belongs to x0 to xn, that is some value within the interval, and the entire term is derivative of order n plus 1. Now, if you look at the observations, the error depends on higher order derivatives of the function. The further x is from the known data points, the larger is the error. High degree polynomials may result in oscillations, particularly at the ends of intervals. That is the Run's formula. Moving on to finite differences. Finite differences are used to estimate derivatives and are essential in formulating Newton's interpolation formulas when data points are equally spaced. So definition would be, let we consider h be the uniform spacing between the consecutive values of x. So the forward difference, let's say fd, will be delta yi equals yi plus 1 minus yi. And the backward difference, let's say BD, is inverse delta yi equals yi minus minus 1. And the central difference CD will be equal to yi equals yi plus 1 and yi minus 1. And if we look at successive differences, that will be delta square yi equals to delta yi plus 1 minus delta yi. Whereas inverse delta square yi will be equals to inverse delta yi minus inverse delta yi minus 1. These differences are organized into different tables for efficient computation. Next is Newton's forward interpolation formula. It is used when data points are equally spaced and it is suitable for interpolating values near the beginning of the dataset. The formula for this is fx equals y naught plus u delta y naught plus u minus 1 divided by 2 factorial delta square y naught, and this continues up to u minus 1, and then it continues to u minus n plus 1 4 divided by n factorial, then delta to the power of n and y naught, where the u is given by x minus x naught divided by h. The steps for implementation includes, first we need to construct the forward difference table, then we need to calculate the value of u, and after that we need to substitute values in the formula to compute the function fx. Moving on to Newton's backward interpolation formula, it is used when data points are equally spaced and best suited for interpolating values near the end of the dataset. The formula for this is fx equals yn plus u inverse delta yn plus u plus 1 2 factorial inverse delta square yn. It is just similar to the forward one. The main difference is that you are just using inverse delta instead of delta we were using in the forward interpolation formula. Then u plus n minus 1 divided by n factorial, lastly delta to the power inverse delta to the power minus n and yn. Here again u equals x minus xn divided by h. The steps for implementation are constructing the backward difference table, calculating u, and substituting values in the formula to compute the function fx. Next is Lagrange interpolation formula. It is used when data points need to be equally spaced and there is no need to calculate the finite differences. The formula for this is fx equals summation from I equals to 0 to I equals n yi dot li x, where li x equals j equals 0 to j not equal to I to n x minus xj divided by xi minus xj. Each Lix is called the Lagrange basis polynomial, and advantages of this that it is very straightforward for unequally spaced data and each term is independent of other, allowing parallel computation. Disadvantages comes into play when there are large data set and it is not computationally efficient for them, and it must recompute the entire polynomial if a new data point is added. Next is Newton's divided difference formula. It is applicable when data points can be unequally spaced and more efficient in Lagrange when adding new data points. So for divided differences, for first order, it is f xi plus 1 equals f xi plus 1 minus fxi divided by xi plus 1 minus xi. Similarly, for second order, it goes like f xi plus 1 xi plus 2. And the formula is f xi plus 1, comma, f xi plus 2, then minus f xi plus 1, and the whole divided by xi plus 2 minus xi. So the formula for Newton's divided difference is fx equals fx naught minus x naught f x naught minus x1 plus x minus x naught, x minus x1, f x naught, x1, x2. And this continues further based on the number of data points you have. Advantages are that divided difference table allows reusability in this case and efficient when new data points are added. So in conclusion, interpolation techniques are essential tools in numerical analysis and are foundational for approximating values within a range of known data. So understanding the conditions for their applicability, deriving formulas step by step, and practicing with numerical examples are essential for your exam preparations and your computational proficiency. So that's all for this video. In the next video, we will move at numerical integration. And I hope you found this video helpful. And if you have any questions, so please drop them down in the comment section. I would be happy to help you all. And of course, don't forget to like the video, subscribe to the channel and share it with your friends. And I will see you in the next video. Till then, happy learning.